Swayam Prabha. Digital India. Educated India.
Welcome to this another session of our discussion on aerodynamics. In today's class, we will continue with our discussion on lift-induced drag. As you remember, we have talked about various sources of drag on our aircraft, primarily the aircraft wing. So we have talked about skin friction drag. We have talked about pressure drag due to flow separation. For at high subsonic speeds and of course supersonic speeds, we have talked about wave drag. And right now, in the previous lecture and in today's lecture, we will be discussing lift-induced drag. You understand that lift-induced drag is something that comes into play when we look at a finite wing that has a pressure difference, between the upper and the lower surfaces. What happens is when you have the pressure difference, so whenever a wing is lift, we have a pressure difference. The lower surface has higher pressure on the average, higher upper surface has lower pressure. And then at the wingtips, flow has a chance of leaking from the high pressure side to the low pressure side. And then if you look at the aircraft, you will see these counter rotating vortex trails that are being shed from the wingtips. Now we have talked about the effect of these wingtip vortices, which is to create a component of velocity, which we call as induced velocity. We also call it, the downwash. We will see because of the direction in which the vertical component of that induced velocity acts, and the effect of that is to tilt the lift vector by an angle, which is known as the induced angle of attack, and we will see that that leads to a drag component that, since that is generated due to lift, we call it lift-induced drag. Now I will switch on to the presentation mode. Okay, and so this is a slide that we have already covered in the previous lecture. So again, lift-induced drag comes from the finiteness of the wing. See here, the wing has a finite termination point, so it's known as the wing tip. This is known as the root that is attached to the fuselage, and this is the wing tip. Okay, so that is on the starboard side or from the port side, the place where the wing ends. That is essentially your wing tip, and you see that because when a wing is generating lift, of course, when a wing is not generating lift, we don't have this high pressure, low pressure difference. Then of course you don't have this flow leaking from the lower surface to the side to the upper side, and then, but when you have that, so when a wing is generating lift, of course you have a pressure difference between the two surfaces, upper and lower. That is the reason why that net force is being generated. However, at the wing tips, as you can see here and here, the high pressure side and the low pressure side has a way of are exposed to each other, so flow can move from the high pressure to the low pressure. Pressure is a motive force, just like voltage drives current, pressure drives flow or mass flow or volumetric flow. So you have a flow that leaks from the lower surface to the upper surface around the tips of this wing. And if you see from a distance, you see these kind of trailing vortices. You can render these vortices visible. So as flow moves from the high pressure lower to the low pressure upper surface, you superimpose the free stream velocity on top of it. You have these counter rotating vortex, trailing vortices, and this can be rendered visible by the use of smoke. We saw a wind tunnel experiment picture in the last lecture. So these vortices can be rendered visible using smoke, and sometimes in real applications, because of the pressure that becomes very low in the core of these vortices, you can see that you have condensation, which renders these vortices visible. Okay, so sometimes you do not need smoke. The condensation actually allows these vortices to be visualized. Now we said that in the Lanchester model, we just talk about these two trailing vortices, but in the Prandtl's lifting line model, you will have trailing vortices throughout the span, of course, of varying strength. So when we said in the strength of a vortex tube, we essentially mean the circulation developed around the vortex tube. So we will see all those considerations in the later slides. when these kind of trailing vortices happen, these vortices actually pull or drive air in because of the movement of the circular motion of this vortices produces a motion around them, and as a result, your velocity field in the neighborhood of these vortices gets influenced by the circulation that is being generated in these vortices. As a result, it can be seen that if you look at the the path line of a parcel of air moving over the top surface, you see because of this movement of air like this, your top surface has flow deflection from the tip chord to the root chord. Okay. On the other hand, in the bottom surface, since flow is moving outward, you see that on the bottom surface, your path lines would behave something like this. Okay, so from the root to the tip. Now, we also saw this slide. That is, this is where these vortices are getting visible because of smoke that has been injected upstream. You see, these are smoke lines that have been injected. So the streamlines, or even you can talk about it as the path lines that are getting visible due to the smoke injection. And you can see that the smokes are actually getting sucked into these vortices, and you see these trailing vortices rendered visible in this experimental approach. Now, as I said, if you look at these, if you look at the circulation that is induced, if you look at the vorticity field that is generated, it can be shown that you can represent these trailing vortices by vortex tubes or by vortex filaments that are directed like this. So these vortex filaments are directed like this, and the strength of the vortex given by the circulation generated by the vortex is same as whatever circulation you have here. Okay, so as long as you match this one and the direction is set such that your vorticity vector is in this direction. So if you take a plane and you try to figure out the vorticity vector, you will see it is in this direction. And just like we have streamlines, there's something called vortex lines. We will talk about it in the next after 2 or 3 slides. So once you figure out the direction of the vortex lines, which are along the vorticity vector, so essentially just like streamlines are such that tangent to a streamline at any point gives you the direction of the velocity at that point. Vorticity lines are such that the tangent to the vorticity line, just like streamline tangent gives you direction of velocity vector. This vorticity line, the tangent to a vorticity line, or vortex line, gives you the direction of the vorticity vector. So if the vorticity vector is directed like this, then you can think of this as the vorticity line, just like the streamline. And collection of these vorticity lines, or rather, like a tube bounded by these vorticity lines, will become your a vortex tube. And if you think of if you shrink it down, because this vortex tube can expand, can reduce in cross section, and we will see that there is something called the conservation of the vortex strength, which forms the basis of Helmholtz's vorticity theorem, and it follows from the divergence-lessness of the vorticity field. We will see what that means. So actually, let me skip a few slides and talk about that before I get into. So if you see, this is a vortex line. Okay, this is the vortex line, and the tangent. So if you see, so vortex line, just like streamline, a vortex line is a line such that if you draw a tangent at any point, it gives you the direction of the vorticity vector at that point. Okay, so that's the vortex line, and it is similar to the streamline. And the equation, of course, this is something similar to the way you figure out the equation for the streamline. You remember that we did V cross dl is equal to 0 to find the equation of the streamline. Okay, streamline is something that is along the local velocity vector, so the cross product will become 0. On the other hand, vortex line, instead of V vector, you now use the vorticity vector, and that leads to a similar kind of equation. In case of the streamline equation, we had dx by u is equal to dy by v is equal to dz by w. Here we have the xyz components of vorticity. Okay, so you think of it as a hypothetical line. such that a tangent to that at any point gives you the local direction of the velocity vector. Now, if you think of, so this is a vortex line. So map it to what you have read or seen in for the streamline. Okay, so vortex line, you can take a few of these vortex lines and define a vortex surface. You can have vortex surface that bounds region, generating a vortex tube. Okay, you see that on this side there is a cross section area C1, on this side there is cross section area C2, and the surface you can say CS essentially defines a tube. This tube will have strength. It depends on the circulation that is established around it, and it actually can be given by this value, vorticity times the cross section. So this area has to be normal to the vorticity direction. So it's a product of this vorticity and the area, and you get the circulation. And it can actually be shown that this value, vorticity and the product of the cross section area at this point will be same as the product of vorticity and the cross section area at this location. Okay, so essentially the strength of the vortex tube is conserved. Now, if you have a region where your C2 has shrunk to a very small number, so if C has gone to 0, your vorticity will increase indefinitely, so that the product still will be the same. So that's the way the strength of the vortex tube is conserved, and we will see that this follows from that divergencelessness of the vorticity field. So this is a vortex tube. This one is a vortex tube of a smaller cross-sectional area. This one is a vortex filament, which essentially means that this is a vortex tube whose cross-section area has been shrunk to an infinitesimal amount. But the strength of the vortex tube, if the strength here was this, if the strength here was this, then by shrinking it to this infinitesimal value, even though your C goes down, your strength of this, the vorticity strength goes up, so the product still stays constant. And if you think of the trailing vortices that we have talked about, so here we are replacing the, so you have to find the direction of the vorticity and hence create the vortex tubes, and the strength will be same as the circulation generated by this. And it can be shown that you can represent this. So we are interested to find the effect of these trailing vortices. Okay, so of course you cannot replace these trailing vortices by this vortex filament just per se, but since we are interested to find the effect of these trailing vortices in terms of the local relative wind, so this replacement is justified. So it models the effect of these trailing vortices on the on modifying the relative wind direction, we will see. So once again, these are vortex filaments. The circulation is same as what is developed in this, and you cannot just draw a filament based on. So you have to understand the direction of the the vortex lines, etc., to create the filament. Now we have this trailing vortex represented by a vortex filament. Trailing vortex represented by a vortex filament. The wing, so we can replace the wing by a bound vortex, which if you remember, this kind of starts, if you remember the starting vortex discussion that we had during the Kelvin circulation theorem derivation. So then you see there is a horseshoe vortex that we have created. Okay, so trailing vortex 1, bound vortex, trailing vortex 2. So essentially we have created something known as the horseshoe vortex, and here we are talking about a single horseshoe vortex. It will be seen that in real applications, we will have a distribution of horseshoe vortices, and that will be brought in because your circulation around this vortex line and circulation around this vortex line and circulation around this vortex line or filament will be, okay, sorry, I think I'm confusing. So vortex line and vortex filament. So these are the vortex tubes, you can think of it that way. And the vortex lines are are aligned with them. Okay, so that's why we get a straight vortex tube or vortex filament. So nonetheless, the strength of this vortex filament, strength, the bound vortex here, strength of the bound vortex here, strength of the vortex filament on this side will be the same. Okay, that will be as per that divergence less on of the vorticity field. And if you want to precisely model it, you will see that the circulation at these tips goes to zero because there is no pressure difference. So for this model, my circulation is constant up to the edges, and then the circulation is contained in these lines. Okay. However, in real, more appropriate models, our lift at the edges becomes zero because there's a way for pressure to communicate from the top and bottom surfaces. So there is no pressure difference at the tip. So there is no lift, hence there is no circulation at the tip. So circulation decreases from a maximum at the root to zero at the tip. So somehow that loss of circulation, remember we said that the product of vorticity and the cross section will remain constant. So if circulation is decreasing, so that circulation is actually put into other horseshoe vortices. We will see that in the subsequent slides. Okay, so since lift-induced drag stems from lift itself, so I have a little bit of recap of what is lift. This will also be something that we will start with in our discussion of when we talk about when we get into the discussion of lift in particular. But this is something that we have discussed, because of course there is no way around it. Everything stems from the pressure distribution and the shear force distribution around the wing. And we kind of talked about this thing when we talked about the lift and drag being normal and along the direction of the relative wind. So here you see that pressure distribution is the source of lift. This is quite easy to understand and appreciate. So this is V infinity. Keep in mind that V infinity is the fast stream relative wind, because as the flow comes close to the airfoil, and remember that we are still talking about that most of these discussions are relevant for that low speed incompressible flow fields. Okay, in fact, this whole Kutta theorem, if you look at the derivation of this, you will see Bernoulli's theorem is being used at some point. So this is the circulation theorem, or the circulation theory of lift, is primarily used in the low speed incompressible flow regime. Okay. In case of your supersonic flow fields, etc., we use the shock expansion theory and other approaches that are used to justify the pressure distribution. Here we don't have shock waves, so it's all about the fluid acceleration and deceleration. Essentially, the velocity of the flow creates the pressure distribution, and that is explained through the circulation theory. Now you see that the pressure distribution around the wing is such that the pressure on the top surface is lower than the pressure on the bottom surface. Hence, there is a net force. And we have emphasized many times by now that this force of lift, or rather the lift force, is the component of the resultant force. See, if you look at this pressure distribution, you get a resultant force, maybe something like this. And then you take the component that is normal to the relative wind. And this one, if you are, if you think about it, as the flow approaches the airfoil, the relative wind, the flow field around the wing now, deflects. The flow moves away from the wing. Remember, it's a subsonic flow, so flow adjustment of direction happens much ahead of the wing. Okay, you will see that in supersonic flow fields there is some problem with this adjustment, because since the vehicle is moving at supersonic speeds, or rather V infinity is supersonic, the information about the presence of this body, which is communicated to upstream in the form of small disturbances or acoustic waves. In case of subsonic, acoustic waves can travel up front because sound speed is faster than U infinity. So the flow can adjust, and as the flow comes closer to the airfoil, it deflects and makes way for the airfoil. But in supersonic, since disturbances cannot propagate upstream, because the U infinity is much faster than the A, or the local speed of sound, so this adjustment does not happen the way it happens in subsonic flow. You have sudden adjustment across a shock wave, etc. Downstream of the shock wave, you might have subsonic flow depending on the kind of shock wave that is generated. But nonetheless, right now we are still focusing on low speed flow fields or low speed vehicles. As you can see, the pressure distribution is created primarily due to the velocity distribution. And we will show that the velocity distribution is really a superimposition of uniform flow with a pure circulation. And that is what generates the lift. Okay. We will talk about these things when we get into the details of lift, the lift portion of our discussion. So here we see that pressure distribution is the source of lift. It can be shown that, I think we have talked a little bit about this kind of approach when we talked about the control surface deflection up and down and how it creates, the forces that are used for changing the angles, the yaw angle, pitch angle, and the yaw, the pitch, and the roll angles. So here you see that starting from a V infinity upstream, the wing essentially creates a deflection in the flow leading to a final velocity in this manner. You can see that, here is your V infinity is directed horizontally. Here your final velocity leaving the wing is directed at an angle to the horizontal. And the delta V is essentially, if you think of the momentum that is imparted to the flow, you can see that the wing imparts a momentum in this direction. And in return, being action and reaction being equal, the wing in turn has a force that is acting in the direction opposite to the direction of change of momentum of the flow field. And this is another way in which you can think about lift. There is some discussion about is this the source of lift or this is the cause of lift, but nonetheless, it's something that is associated with lift. Now there is the circulation theory of lift. So this is lift. You can justify lift from just the pressure distribution. Here you can justify lift as a reaction to the change of momentum of the surrounding fluid. On the other hand, it can be shown, and eventually we will learn about this thing in our detailed discussion of lift, that there is something called the Kutta-Joukowski theorem that relates lift to the density, velocity, and the circulation developed around these wing cross sections. And it will be seen that, so we will again with these incompressibly rotational flow fields, we will use something called the velocity potential formulation, because if it is a rotational field, then velocity can be represented as the gradient of some scalar, and that's the velocity potential. And we will see that starting from that idea of velocity potential flow over a rotating circular cylinder, and then applying Bernoulli's theorem to find the pressure distribution around the cylinder. And then, of course, lift is just the effect of that pressure distribution. It can be shown that lift on that rotating circular cylinder is something like rho infinity V infinity times the circulation. And it can be further shown that through suitable transformations, the same lift is actually generated for cross cylinders whose cross section are not circular. Okay, so first we show that for a circular cylinder, lift is equal to rho infinity, V infinity, and circulation. Also, keep in mind that in real world applications, the amount of circulation, so the amount of circulation is such that there is a condition called Kutta condition. That is, if you have too much circulation, your stagnation point can come to a lower surface. If you have too little circulation, you might have a stagnation point on the upper surface. But in nature, it is always seen that the amount of circulation is just right so that the flow leaves the trailing edge smoothly. Okay, so that sets the amount of circulation, and we will see all these things. Okay. So also there is, if you think of an experiment, we talked about this thing during our discussion of the Kelvin circulation theorem, that as you start a wing, you have a starting vortex, you have a bound vortex. The strength of the bound vortex is such that the flow will leave the trailing. Okay, this is difficult to prove it theoretically, but it is always seen experimentally that flow leaves the trailing edge smoothly. There is essentially that sets an amount of circulation. So to have the flow leave the trailing edge smoothly, you need a certain amount of circulation, and then that is what generates quantifies the amount of lift, because rho infinity, V infinity are more or less are your free stream conditions, and the amount of circulation will be such that it will it will satisfy the Kutta condition. And so now if you remember what is the circulation, all you have to do is draw a hypothetical boundary, and there all you have to do is figure out what is at every point, figure out the direction between the local dl vector. Dl is just a small element of that boundary, the local velocity vector, and work out this integral. Okay, so v dot dl across the entire contour, and you will see that will give you the strength of the circulation, or also the strength of the vortex that is being generated somewhere. So whenever you have a non-zero circulation in a bounding curve like this, it means that inside there is some vorticity going on, and that is, if you remember this formula, so circulation is, you can work out a line integral of velocity dot dl, and it is equal to the surface integral of the vorticity dot ds. Okay, so if there is some vorticity in this region such that dot ds is a non-zero value, then you can have a non-zero circulation. Sometimes it might happen that you have positive vorticity, negative vorticity that are cancelling out, and you get no net circulation. But that is another, for some other discussion. So here, when you have a positive circulation, it means inside there is somewhere there is some vorticity. Now it can be a singularity. We will see that it's a irrotational vortex for this particular circulation field that is developed, and it can be shown to be a superimposition. So this flow field is actually a superimposition of an uniform flow plus a pure circulation, and you see that is the reason why flow on the top speeds up, flow on the bottom. So when you add this with this, flow on the top is on the average faster than the flow on the bottom, and the pressure difference is created that way. Now, if you look at this, you remember we talked about replacing the wing by a vortex filament of strength, equal to this strength of the bound vortex. And you see the direction of this vortex filament is aligned with the direction of the local vorticity vector. So this is like a cross section of what you see here. So this picture here, say A is nothing but a cross sectional slice of this region. Say we call it AA. And if you think of the vorticity, it is directed along the span. So your vortex filament is also directed along the span. And the strength of this vortex filament is same as the strength of circulation. So you can compute this circulation. Strength of circulation is same as the strength of the bound vortex. And as I said, that the strength of this is such that the Kutta condition is obeyed. So at this point, we have a bound vortex that is represented by this vortex filament, whose strength is same as the strength of circulation required to have the flow leave the trailing edge smoothly. On the other hand, if we see these lines and these lines, for the single horseshoe vortex approach, whatever strength of circulation we have here will actually be here because of that the cross section. So the inflow of vortex so essentially it's a product of, so the inflow of the vortex filament strength is equal to the outflow of the vortex filament strength. So if you have inflow here, then the outflow here will be the same, and we will show it what is this inflow and outflow. If you remember, it is essentially this thing that we have shown previously. So depending on how your vortex tube or vortex filament is moving in 3D space, if you take any cross section, area C1, area C2, then the circulation here will be same as the circulation here. And this is because of the divergence less of the vorticity field. And we will see this thing. So what will happen is here, since we have no other vortex filament, whatever is here will go into this one. However, if you have a vortex, if you have multiple vortex filaments like this, which is part of the Prandtl's lifting line approach, what happens is you have a vortex filament that comes like this, and then you can think of a portion of the strength. Essentially, so this is C1, so this is C2, and this is C3. And what will happen is the strength of the filament here will be the addition of the strength of the filaments here and here. Okay, we will see those things in the subsequent slides. Okay, so this is also something that we have shown in the previous lecture, that is contrails represented as vortex filaments, so strengths match the circulation generated by these contrails. The trailing vortices induce a velocity field at different locations of the wing. This is known as the downwash. For the single horseshoe vortex case, that downwash distribution looks something like this. On the other hand, we said that in reality, however, you have vortex filaments or trailing vortices that are actually shed all over the span. But eventually, you see the vortices as they are shed from the trailing edge across the span, they induce some velocity field and they influence the movement of one another. In fact, there are some very interesting visualization studies of vortex rings generated by a vortex generator, and there you have multiple vortices that are being shed, and you can see how the trajectory of different vortex rings are being influenced by one another. Okay, so these vortex, the contrails and the contrails throughout the span, they induce the velocity or influence the velocity of each other, and eventually they roll up into this kind of vortex sheet. So the two ways of looking at it are kind of similar. Only in Prandtls, the near field effect is properly modeled. In Lanchesters, the far field effect is properly modeled. So we will see that for a single horseshoe vortex, this is the distribution of downwash. And this is whereas if you have a continuous, if you have a series of contrails, then what will happen is your downwards distribution will be different, because of course you have to take into account then the effect of each of these vortex filament on the downwash, and run a addition. So here you find the downwash here due to this one. And remember, we talked about the Biot-Savart rule, and I said that if you are really interested in figuring out how that is derived, you can go into Karam Chetty's book. Nonetheless, so this trailing vortex would induce some downwash here. This trailing vortex or the vortex filament will induce some downwash here. And if you do the vectorial addition of these two, you will find the downwash, so something like that. On the other hand, here you have to do that for each and every vortex filament. So if you want to figure out what is downwash here, you have to then take into account the downwash there because of each of these trailing vortices. Okay, so that's a difference between the single horseshoe vortex model and the like a superimposition of many horseshoe vortices. So you can think, for example, you can think of this as a horseshoe vortex like this. This one is horseshoe vortex like this. And then you have many horseshoe vortices, and then you can figure out the induced velocity as a result of that due to each individual horseshoe vortex combination, or the sum total of velocity downwash due to each individual vortex. This is also something that we have discussed in the previous class. You can find the effect of the velocity field induced at a location using so this is the Biot-Savart law. And this is the Biot-Savart rule that is useful for our discussion, because remember, for us, our vortex line, so here the vortex line, or rather the vortex filament, is curved and it extends from minus infinity to plus infinity. On the other hand, here my vortex filament, because see, I am interested to find velocity field induced here by this straight line vortex filament. Okay, of course, in this case, we have multiple straight line vortex filaments. Okay. So then what becomes more useful for us is to look at a vortex semi-infinite straight line vortex filament extending from A to infinity. So if you think of something like this, so this is your A, this is infinity. And then you are interested in finding the velocity field induced at V due to these vortex filaments. So suppose this is my point P, and you see this is 90 degrees, so that's 90 degrees. And then we can use this formula to find the velocity field induced at the location P due to that entire semi-infinite straight line vortex filament. Okay, so if you work it out, you get something downwards distribution as shown here for a single horseshoe vortex. As you can see, downwards distribution along y-axis. So y essentially then is this axis. So downwards distribution along y-axis, and you can see that this is just a way in which these things are, the nomenclature is C minus b by 2 to plus b by 2. So your span is b, semi span is b by 2, and span is, so essentially if you, so this line is just a vortex filament replacing the real wing. Okay, because the purpose of the real wing is to really generate that bound vortex. And then from the Kutta theorem, you know that lift is equal to rho infinity u infinity times circulation. So here the circulation generated by the bound vortex. So you can replace the bound vortex. Essentially, this is the effect of the wing. Okay, so this is a vortex filament whose strength is same as that of the bound vortex, and the lift is then rho infinity u infinity times the strength of the bound vortex. Now, so this is the way to find induced velocity due to vortex filaments. And here, this is something that I have hand-wavingly introduced. So you will see that there is something very important to observe here, which is this aspect, and that is the basis around which that Helmholtz vorticity theorem is found. So what happens is, okay, let us quickly look at some of these, whatever I have scribbled on this page. So for incompressible fluid flow, we have seen that this rule holds. Okay, so the divergence of the velocity field is 0. Vorticity is defined as the curl of the velocity field. Okay, so this is the cross product. On the other hand, this is the dot product. So curl of the velocity field is vorticity. Since vorticity is the curl of a vector field, the divergence of vorticity field is 0. So this is an interesting result from vector calculus, or just from vectors. That is, since vorticity is defined as the curl of a vector field, the divergence of vorticity itself becomes 0. Okay, so now consider these two important other vector identities. Okay, so these are vector identities that you can find in Anderson chapter 6. Well, these are the equations 6.1 and 6.2. I think these are from Anderson's Fundamentals of Aerodynamics. The other book also has some overlap, the Introduction to Flight. So you can kind of try to see which book this one is from. So you see that the surface integral of A dot ds, so a vector surface integral. So you see these are ways in which we move from surface integral to volume integral. Okay, so this is a vector. So A is a vector and ds is the vector surface element. And we see that if you want to calculate the A dot ds over the surface S, that is same as the divergence of A vector over the entire volume. On the other hand, if you're looking at a scalar distribution, so here phi is a scalar, not a vector. So to evaluate the surface integral, you can also run the vector volume integral of the gradient of phi. So this is a way in which you move from the surface integral to the volume integral. Okay. So now if we replace this A vector by the vorticity vector, then what do you get? So we invoke this particular thing. Okay, so over a closed surface S. Okay, so that is the sign for a closed surface. So over a closed surface, this product, so this thing, just replace A with the vorticity vector, is same as the volume integral of the divergence of the vorticity. But we said that the divergence of the vorticity field is 0 because vorticity is the curl of a vector field. So then what happens is this thing, the surface integral of your vorticity dot ds becomes 0 over the entire surface. Okay, so closed surface. So now you can think of, let's think of this one. Okay, now look at this one. So we just said that because of the divergence lessness of the vorticity field, this thing will become 0 over the entire the surface that is bounding the volume. So here your surface, this surface is bounding this volume. So what you see here is, now we look at a vortex tube. It doesn't matter, it can be a vortex filament as well. Just the cross-section area is shrunk to 0. What you see is this thing is 0 over this entire closed surface. Okay, so C1, C2, and the CS, which is the surface of this vortex tube. So what you get is C1 this plus C2 this plus CS of this. Now, by definition of the vortex tube, these are the vortex lines. So the vorticity here is actually 90 degrees to the ds field. So this thing becomes 0. So what ends up happening is this integral becomes same as this integral. So if you have taken your C1 and C2 such that these are normal to the, so if your vorticity field or vortex lines are such that these lines intersect C1 and C2 at right angles, or rather the surface normal is along the vorticity direction at C1 and C2, then you can just say this thing equals to this thing is equal to the circulation. So flow vorticity through any cross-sectional surface of a vortex tube is a constant all along the tube at every instant of time. So given an instant of time, your this product of the vortex strength at C1 is equal to the vortex strength at C2 is equal to vortex strength at C3, etc. So what this establishes is, if you have a situation where you have a vortex tube like this, the only way the strength of this tube can change is if you shed some strength along some other tube. Okay, so otherwise your strength has to be conserved. So in case of the single horseshoe vortex, if you have a bound vortex filament of a given strength, then as you bend that vortex filament, the circulation strength here and the circulation strength here will be the same. Okay, circulation strength here will be the same because if you use this rule. Okay. However, if you have these multiple vortices that are being vortex contrails that are being shed, then you see that this strength will add up on this, then this strength will further add up on this, and eventually you can have a circulation distribution something like this. Okay, so we will see these things: circulation distribution or the strength of the vortex filament. Okay, now let me. So once again, I think this is something I do not need to emphasize here, that your angular velocity is half of the curl, and that follows from something like what we have discussed in these slides. Okay. It depends on how you define that, that angular. So how you define that angular velocity, and it can be shown that if you take it half as the rotation of these two mutually perpendicular sides, then you can show it to be related like this. On the other hand, this is something that will become very important when we start working on the lift portion of our discussion. So here, see, I have used circulation at infinity. It really doesn't matter as long as the the geometry or the right circular cylinder or the the airfoil shape is enclosed by that bounding curve around which I am evaluating my circulation. I think this will be the same thing. So, okay, so now with these two ideas, that is the vortex filament strength is conserved across cross sections, and secondly, that the lift is related to rho infinity u infinity times circulation, you can now see that, so because circulation, remember, circulation is nothing but the strength of the vortex filament. So there is something to do with lift, circulation, and the vortex filament induced velocity field in the neighborhood of the wing. So we will now get into that part of the discussion. So this is just to establish that the vortex strength of the filament stays conserved as you go from one cross section to another cross section at any given instance of time. So this is again, like to summarize what we have been talking so far. Here you see, I have a vortex tube. I'm calling it A. I mean, vortex filament would just be that your C tends to 0. So here C1 and C2 are finite, and is a vortex tube of some strength given by the circulation, gamma A. So this is a vortex tube whose one end cross section is C1, the other end cross section is C2, and the strength of that vortex tube is given by gamma A. Now keep in mind that if these, this thing has to be conserved like this, then you cannot have a sudden termination, because then this inflow of vorticity multiplied by cross section area, outflow of vorticity multiplied by cross section area will not hold. So what will happen is a natural consequence of that requirement makes, kind of brings us to this idea of vortex tubes cannot just exist in isolation like this, okay, because it cannot terminate like this just by itself, because your inflow and outflow of that vorticity strength, or rather the product of that vorticity times the area, will not be conserved, okay. So what will happen is here your vortex tubes by this requirement would extend from -infinity to +infinity, so they cannot have a sudden termination, because if they terminate suddenly, then what happens to the outflow and inflow balance? So these vortex tubes would typically extend from -infinity to +infinity. In some cases, you can think of a loop. Okay, so dolphins and some other aquatic animals, they have this. You can look at these dolphin vortex rings generated by dolphins, and etc. So there you see that you can also have a vortex tube that ends into itself. So that way the conservation is again honored. Okay, so you can take any cross section and you can show that maybe your cross sections are changing, but then your local product of that eta 1, eta 2, eta n. So maybe this is A, this is B, this is C, and you can show that eta A cross section area at A is the same as eta B cross section area at B, etc. You can have a semi-infinite vortex tube. Of course, then one end terminates abnormally. Okay, so for example, it can terminate on a solid boundary or something like that. So these are some nuances associated with Helmholtz vorticity theorem, and this really follows as a consequence of the divergence less of the vorticity field, as we have seen. So here again, you see that if these are not equal, then somehow you have shed something. So the vortex tube has bifurcated or trifurcated, and the strength has been adjusted accordingly. Okay, so this thing. Here again, there is no bifurcation or no side loops or something like this. Here you have a branch off point here. And again, this all can be justified based on this argument. For lines along the stream tube, the vorticity vector and the surface normal are at right angles, so that becomes 0. Only these things where the vorticity vector and the surface normal are aligned with each other, we have non-zero. That way these things can be shown. Now, why are we talking about all these things? We look at this picture. So see, the circulation here is constant, and then it goes to 0, and that circulation strength is now contained in these vortex filaments. So strength of the vortex filament has now become in this vortex filament. On the other hand, in more real settings, your lift at the edges becomes 0 because there is no pressure difference. If lift becomes 0, then circulation at the edges becomes 0, because if you remember, lift is equal to rho infinity u infinity times circulation. So if you think as the lift at various spans, like span-wise lift distribution, then at the tip chords you have no pressure difference, hence no lift, hence no circulation. So this is a more realistic distribution of circulation. So you can think that circulation goes to 0 here because no pressure difference, hence no lift. If no lift, then no circulation because rho infinity, u infinity are still there, right? So to make this 0 at the wingtips, your circulation at the wingtips will be, you can force them to be 0, and then eventually you will see that a distribution like this follows. Now to generate this distribution, you can show that you can have a series of contrails all over the span. Of course, they will eventually get sucked into these two major trailing or wingtip vortices, but in the neighborhood of the wing, you will have a series of these contrails, and we will see how this distribution is justified by the use of all these contrails. So this is what we do. So if you see that the sequence of contrails instead of just two, what we do is we say, remember our circulation has a distribution something like that. So what you can do is you can think of various horseshoe vortices that are aligned like this. You see that the strength of this filament, so you can think of like just one filament, is a superposition of, like say in this region, at the root, not the tip, at the root, here the circulation along this span direction will be a superposition of the circulation created by each of these horseshoe vortices. Whereas in this region, the circulation along the span is just contributed by this portion of this horseshoe vortex. Okay. For example, this one is not contributing to this one. When instead of finite number of horseshoe vortices that are superimposed to generate this distribution of circulation as we find in the real vehicles or real finite wings generating lift, if you just increase the number of horseshoe vortices to infinite number, then you get a smooth distribution such as this, and the strength of a vortex filament or vortex tube is nothing but the rate at which the circulation is changing multiplied by the extent over which your this filament extends. Okay, because that strength of that vortex tube has to be brought into this trailing vortex, the contrail. So this one just gives you the difference between this level and this level, and then this difference of strength has to be shed along the vortex filament, so that the next vortex filament can match to the whatever circulation is at this point. So if you think of the finite or the finite version or the finite number of horseshoe vortices, you can see how the strength of these things relate to the change in these levels. So if you just make it infinite, it can be shown that the strength is nothing but the rate at which just d by dy of the circulation multiplied by the thickness of this element. So that much circulation strength is actually taken up by this particular line vortex. Okay, now to find the velocity field induced, what we do is suppose. So at this point, we want to find what is the velocity field induced by this vortex tube. So the vortex tube is at a location eta, thickness of or diameter is d eta, and we want to see what is the downwash induced at this location y. Okay, so this is the span-wise direction. You can see plus b by 2 to minus b by 2, which are the semi-span. As I said, the span is b, semi-span is b by 2. So it can be shown that the downwash at location y is given by this integral, and this will follow. It's quite simple to see that if you remember that Biot-Savart rule specialized to the semi-finite. So essentially, this one is, if you remember this diagram here, Okay, if you remember this diagram, essentially we are making use of this rule. So due to you find the downwash at a location like this, and this is your semi-infinite vortex line. So if you think, so this is the semi-infinite vortex line. So here, this is your semi-infinite vortex line. So this is your semi-infinite vortex line. This is, this is a termination. So it starts from here. See, it's not a termination. It's the your vortices that are extending in this direction along the span. So if you use the Biot-Savart law for the semi-infinite straight line vortex filament, you can get the induced velocity at the location y here, and the strength of the vortex, filament here is given by d gamma dy. So this one, sorry, d gamma dy, and here my eta is along y, so it doesn't really matter. So you can get the strength induced at this location. Now what happens is, if you calculate the induced velocity or the downwash at each of these locations, something very important comes up. What happens is, if you see here, so this is a slide, perhaps we will continue in the next class as well. So you see what is happening is, so this is my V infinity direction, okay? So this is my V infinity direction, or rather say this is my V infinity direction. So this is, I'm looking at a particular cross section of the wing. Okay, so you have the finite wing, and I'm looking at this one particular cross section. So V infinity is the relative wind coming towards the wing, and from a far off distance, of course, we are seeing, okay, V infinity is what is coming to the wing, but because of these the downwash created by the distribution of those horseshoe vortices, we have this small, this relatively small downwash is there compared to V infinity. So there is a that W is known as the downwash velocity, and what it is doing is it is superimposing itself on V infinity and tilting the local relative wind. So V local, so V infinity, we have talked about as the relative wind, but for finite wings, because of the contrails, you can have just, from the Lanchester model, 2 contrails from the wingtips, or from the Prandtl's lifting line model, you can have entire series of these contrails, and they induce a W at a given, span-wise location, and that tilts the, or rather creates this local relative wind. So this is an important concept in understanding lift-induced drag. So a local relative wind is created, and now what will happen is, you see that your lift, if you remember, is at a right angle. So this is normal to the local relative wind. Okay, so local relative wind is tilted by an angle alpha I, so it's called the induced angle. Okay, so this is called the induced angle, and we will see some rules over here. So since the relative wind is tilted by alpha I, your lift, which was like this for the infinite wing, has now been tilted like this for the finite wing. Okay, because that cross section has a given circulation. Your relative wind has been has moved by an angle alpha I. So the lift generated, which is now rho infinity, V local, or this is not exactly the local, we call it the relative wind. So for the wing cross section, because of the induced velocities downwash, your relative wind has now become slightly different. Okay, so now for that relative wind, my lift vector is now, it is rho infinity u infinity, because that V local and V infinity are almost same in magnitude. Okay, that W is really small. So what is happening is, my lift is not changing much, but it is rotating by an angle alpha I. So then what we can say is, this is my new direction of lift normal to the local relative wind, which is a superimposition of W and V infinity. And then if you take a component of these, so when you're looking at the aircraft flying, from a distance, you still are talking about lift as normal to the global V infinity. So what is happening is this is still the lift with respect to the global V infinity, okay, not the local V infinity. So then you have, with respect to that global V infinity, this is still the lift, but now we have this a drag component because of this L. Okay, and that is given by L. So induced drag di is L times sine alpha I. Okay, sine alpha I. So this is my induced drag, and that is really because of the tilting of the lift vector by an angle alpha I, which happens due to the downwash that is induced by the contrails. Now this can be single or it can be distribution of contrails. This alpha I is really small, so you can just say L times alpha I, since alpha I values are typically small, etc. But nonetheless, I think we are out of time for this lecture, so we will continue our discussion of this in the next class, and then we will perhaps move into a discussion of something very interesting known as the Buckingham's pi theorem in the next lecture. Okay, thank you very much, and see you all in the next class.